very good afternoon, unless it's morning where you are or night time, because that's the thing about space and time. They're all mixed up and confused in the real universe. And we'll be looking at time later on. Last session in this series of 6. Whoops, that's Matthew here. That's Brendan. Hello, Brendan. Have we got Brendan? Somebody joining us? Yeah, Brendan Chang. Here we are. Hello, Brendan. You're not Brendan?
No, I'm not Brendan. I'm her sister. I'm his sister.
I thought so. Okay, welcome aboard. Let's we'll crack on. I've just welcomed everyone to say that depending on where you are, it's a very good afternoon or good evening or good morning or whatever it is, because time is a funny thing. We'll be talking about that later. So as someone once said, it's all a matter of wibbly wobbly, timey-wimey stuff. But anyway, thanks for coming along today or yesterday or tomorrow or whatever it is for you from me to find out all about space travel, certainly today, and how space and time are inextricably linked together. Okay. As you can see, I'm speaking to you from my very own space and time ship that I borrowed from a friend. I hope you like it. Space and time have always held a fascination for me. And the great thing is we need to learn about space and time as part of the school curriculum. So that's pretty cool. It's on the syllabus. It's not quite as interesting as it can be because that's school, and school always focus on the boring bits, don't they? You notice that? All the exciting bits, they seem to gloss over, but there you go. So I want to share some of the fascinating and astonishing facts about the universe with you. I hope you find space and time interesting. I think you do because you've chosen to come along on this journey across the universe. So let's just, before we start today's lesson, I'm going to say a little bit about what's going to happen over the next today and the next 5 weeks following. We're going to be taking an imaginary faster than light journey across the universe and exploring what we see as we go. Now, of course, in reality, we can't travel faster than light. If we did, according to Einstein, if we did, all sorts of weird and wonderful things would happen. We would change our mass, time would alter, space itself would become all weird and wibbly wobbly, spacey weighty stuff. And when we came back, we'd probably end up younger than our grandchildren, which is kind of weird, I suppose. Yeah, that would be weird. Yeah. Anyway, I digress. So in the coming weeks, we're going to be looking at the solar system next week. That's the sun and all the planets and assorted rocks and stuff that orbit it. And then we're going to look at our place, the solar system's place in the galaxy. That's one of hundreds of billions of stars in just our galaxy. And there's hundreds of billions of galaxies around the universe. So we'll be looking at, after that, the universe itself, what's going to happen to it, where it's come from, how we can explore it. Bearing in mind that most of us are tied to the planet, we can't go too far away. And then we're going to look at what the chances are, what life is out there, and if it is, what it's going to be like. And then we're going to finish up the last week with a look at the very nature of time itself, some of the weird things that can happen to time. Okay, first we need to be actually able to leave the Earth. So the first thing we need is a craft to traveling. Now, not everyone's lucky as me to have my own space-time ship. So we need to get a rocket. So we need to travel with, and before we can even travel, we need to understand how we can break free from that grasp of gravity, that stuff that holds us onto the planet and keeps us here. And once we can do that, then next week we can start our journey in earnest and have a look at the solar system as we move on. So let's have a look at what we'll be finding about this week. If I can advance the slide. There we go. Yeah, we're going to be looking at space. Oh, that's what we're going to be covering a weeks ahead. I should have done that. We're going to be looking at how rockets work. We're going to be looking at conquering gravity, what gravity is, and some of the problems that we're going to come across if we want to leave gravity. We're going to look at why satellites don't fall down to Earth. And finally, I'm going to run through it with you, but I'm going to point you in a direction of some plans where you can, to relieve the monotony that is lockdown, to build your own rocket. So I hope everyone's got a garden or at least an outside area that they can go and put some stuff in and fire it up into the air. Now, word of warning, the rocket that you build, well, let's just say leaving Earth is potentially hazardous, okay? So don't actually try to travel on the rocket if you build it. First of all, it's going to be far too small, and secondly, it will never get off the ground with you sitting on it, and it might actually do you some damage. But it will lift off if you do it properly. Okay, so how do rockets work? Right. A rocket is not like any other vehicle. It's totally unlike any other vehicle you've come across. Not only does it have to leave the Earth, but it needs to be able to travel vast distances in a vacuum. And it has to be fast enough, has to be strong enough to survive the most hazardous journey you can imagine. The conditions in space are incredibly dangerous. And so it needs to operate at temperatures ranging from sub-zero to those hot enough to melt metal itself. It needs to resist incredible forces that will buckle solid metal and crush rocks. And inside it. Somebody's talking about. I'm just going to mute a couple of people. That's better. Otherwise, I'm going to get a little bit of. That's better. Where were we? Yeah. And all that while protecting the people inside the rocket. Now that requires an amazing structure and a complex system of controls, all at the same time sitting on top of some of the most powerful engines that have ever existed, designed to take that rocket and fire it across the universe, and powered by an immense volume of fuel that's so reactive that it could destroy tremendous amounts of matter if it went wrong. So what sort of engine do we need for a rocket? Now, like most engines, we need a fuel. Rockets burn fuel. And rocket engines, most of them, turn that fuel into a hot gas. And the engine pushes the gas out at the back. And the gas, it's the gas coming out that makes the rocket move forward. So a rocket is very different from a jet engine. They look similar to start with. They have a power coming out the back, but there's a lot of differences between them. For a start, a rocket engine doesn't need air. It can't have air because there's no air in space. So it has to carry everything it needs with it. A rocket engine will work in space where there's no air. So if it needs air, it has to take the air with it. But it doesn't always need air or oxygen. Okay. So there's two main types of rocket engines. Some rockets use liquid fuel. And the main engines on the Space Shuttle orbiter, you can see there. Oh, let's have a look. Let's just have a look at a jet engine first. As you can see, with the jet engine here, on the left-hand side here, you can see that the air comes in. It's compressed using those sort of rotating fans. It's then mixed with the, let's just move these guys out of the way. It's then mixed with the fuel, and that's that produces the energy to turn the shaft, which then blows out the back an exhaust of, in this case, hot air, where it's burned all that oxygen. So it's an incredibly hot, very sort of noisy engine in there. If anyone's ever been anywhere near a jet engine, it's been working. Now, these are the two types of rocket engine you've got. On the left, you've got a liquid rocket, and on the right, you've got the solid rocket. The physics is the same, as you can see underneath, just working out the right. Don't worry about those formulae. That's nothing you need to know at this stage, but it's just to show you that the maths is the same for both. The only difference is you've got fuel, an oxidizer, and pumps with the liquid rocket engine, where they're brought together and they're burned together in the combustion chamber, and that produces the gases, the hot gases that pour out of the back through that nozzle. Whereas on the solid rocket engine, you have a solid fuel with a mixture that oxidizes it, mixes it with oxygen, and then you have a flame, again, which in the combustion chamber burns, oxidizes that fuel, and again produces a gas which pushes that out the back. Okay, so the space shuttle. The main engines on the space shuttle, if you remember from a few years ago, long before you were born, this was the main way we used to get into space. They use liquid fuel. Okay, and the Russian Soyuz rockets, they used liquid fuels as well. But other rockets, as we said, use solid fuel. Now, if you look on the side of the space shuttle there, those two long white things, those were booster rockets. They were used to help get the space shuttle actually off the ground on the first stage of its journey into space. And they are solid rocket boosters. And they use solid fuel, exactly the same way as fireworks and model rockets, also using solid fuel. Okay, so how does it work? If there's no air to push against, if there's no oxygen to burn, we work that one out. We take the oxygen with us. We have to take everything we need to burn. But in space, an engine's got nothing to push against. So how do rockets move in space? Well, the rockets work following a rule called Newton's third law of motion, which you may have heard of. Now, roughly speaking, Newton's third law was invented, if you like, or devised by Sir Isaac Newton, an English scientist, who actually had 3 laws of motion. And they came up with those about 300 or more than 300 years ago. And the first is all about how things either stay still or they continue to move unless a force acts upon them. And the second shows how that applied force can affect a mass by accelerating it. And then his third law, which is the interesting one, basically says that for every action there's an equal and opposite reaction. What that means in practice is if I apply force to something, or you do, then that object that I'm applying a force to will push back on me with equal force. It's how you walk. You push on the ground with your feet and the ground pushes back on you. If it didn't, you wouldn't move anywhere. And if you've ever tried to walk on ice or anything like that, you will realize that you need something to push back on you. Otherwise, you don't move. So if you push something, pull something, or twist it, then that thing that you pull, push, or twist will pull, push, or twist back on you with equal force. So when a rocket pushes back on the exhaust, then the exhaust pushes the rocket too. Okay? So it's a bit like this guy picture you've got on the screen at the moment. If I was on a skateboard and I had a bowling ball and threw that bowling ball forward, then the bowling ball would move forward, but the man on the skateboard would also move back. And the distance that each object moves is related to the mass. So if the bowling ball weighs less than the man, then the bowling ball would move the furthest, it would accelerate the fastest, but the man would still go back. And that is exactly, believe it or not, how a space rocket works. Okay, so in this case, rather than a skateboard, we have the rocket engine. So as you can see, we burn the fuel. It doesn't matter, that front bit is the liquid or the solid fuel. It's burning and it's forcing those gases out through that exhaust at the back. And the exhaust pushes backwards against the, if you like, the rocket itself. And the engine pushes the rocket itself forward. Because, as Newton said, for every action, there's an equal and opposite reaction. And the push forward is equal to the push back. So a bigger force, a more powerful engine, is applied to the motion of the rocket, the faster it's going. That's why rockets have massive engines and require lots and lots and lots of fuel. Okay, just before we move on to the history of rockets, bit of information. If we use the relevant formulae for energy, then we can calculate that to get into space, it requires about 811 megajoules of energy to get into orbit. Now, megajoule is 1 million joules, so that's 811 million joules of energy. And that's excluding any energy loss from air resistance and heat. So it's an incredible amount of energy. You know, if you can think about how much that is, that's amazing. That could power your house probably for the rest of your life if you had an energy source like that. That'd be amazing. We've done the skateboards, so when were they invented? Okay, right. The first rockets, as you can see on the screen, the earliest rockets were used in China. The first records we've got of them being used in the 1200s. They were solid fuel rockets, and they were used mainly for fireworks. But like a lot of things, as soon as the military saw them, they thought, well, we could use those. So they were used by armies in wars. And over the next 700 years, rockets got bigger and more powerful, and they were more efficient. And again, many of those were used for wars as well. In 1969, the United States launched the first men to land on the moon using a rocket. It's called a Saturn V rocket. You can see it on there, suitable for moon launches. Now, all of that rocket was, if you can't really get a scale on that, but it was massive. Now, if you see at the top, there is a little, like a cone shape. That's where the men were, 3 of them inside there. And it was, a lot of that rocket was disposable. That's to say that as it was going up into the atmosphere, then bits of it effectively fell off. They were jettisoned. So let's put you back over there a little bit. That's better. So each stage of the rocket, as it went up into the air, the bottom bit would drop off and fall back to Earth, and it couldn't be used again. It got destroyed. And then the second stage and the third stage, and it was only that top little bit that actually got to the moon. It was incredibly inefficient in that sense. So before we can actually get into space, though, we need to leave the Earth. Now, unfortunately for us, well, I say unfortunately, fortunately as well, there's a force that keeps everything on the ground. It's called gravity. We knew that, didn't we, anyway? But there you go. And it's a good thing, really, that objects don't just float off into space. It'd be quite inconvenient, although, of course, it could actually explain why I could never find anything when I need it in a hurry. So maybe that's where things go. Okay, so we've got gravity holding things down, but where is space? Where does it start and Earth stop? Because if we're going to go into space, we need to know where it is. Now, oops. Ooh, oh, there we go. In order to get there, we need to use our rocket. Now, our rocket is going to need an awful lot of fuel. Now, if we look at the space shuttle, that's some figures on the screen there. That's how much fuel it needed just to get into space. And it actually, the fuel that it carried with it was 20 times more weight than the shuttle itself. So if you think for every kilogram of shuttle, we needed 20 kilograms of fuel. Now, can you imagine if that was the same for your car when you went driving? You'd need 20 times in weight, in mass or weight, the fuel for that car. So if you had a half a ton car, you'd need a 10 tons worth of fuel just to get it going. That's an incredible amount of fuel, really. Okay. So, before we move on to that one, I've just got some figures to give you on that one. Oh, let's go back. That's better. So, about 6,200 miles, that's 10,000 kilometers above the surface of the Earth, that's where the final particles of the atmosphere peter out and it becomes true space. So deep space, true space is about 10,000 kilometers above the Earth. Okay, great. But that's not where we measure space from. The absolute vacuum of space is what you might think of as space, but at 62 miles, somewhat less, 100 kilometers, you go beyond something that's called the Kármán line. Now, what's the Kármán line, I hear you ask? I don't, because I've got you on mute. The Kármán line is the height which is commonly accepted as the start of space. Okay, it was calculated by a Hungarian. Let's have a look. Oh, did I put him in here? I had a picture of him. I haven't put him on my little presentation. That's a shame. Okay. Okay. Theodor von Kármán was a Hungarian-American physicist, and he determined that that was the height which scientists still consider to this day to be where space starts. And that's the height at which an aeroplane, an ordinary aeroplane, can no longer achieve any lift. So to exceed the Kármán line, you need to have enough thrust to leave Earth's orbit, which is usually achieved with a rocket. Now, if you think about that, 62 miles, that's not very far. It's about the same distance from London to Canterbury in Kent. Now, people used to walk that. And if you've ever read the Canterbury Tales at school, or heard of that, you may have read some of those stories in English. Well, I say English, it's a weird sort of English sounding English, but nowadays, of course, a journey of 62 miles would be done in a car, and it would take about an hour, probably a bit longer on bank holiday because of the traffic. So if you think about it, if we could get in a car and drive straight upwards, it would take us about an hour to drive to space. That's how close it is. In fact, if you were to scale down the Earth to the size of an apple, then the layer that is the atmosphere would be about the same thickness as the skin of that apple. It's that close to space. And that's how far we've got to get to say we've been into space. Okay, so gravity. Gravity is the name we give to the force that keeps everything on Earth, all that stuff that stops everything drifting off into space. It's not actually a very strong force, really, and it's quite easy to overcome. You do it every day. Every time you stand up, every time you pick something up, you're defying gravity. Or at least you can for a short while. And anyone who's ever jumped, oops, keep pressing the wrong one. Anyone who's ever jumped, climbed stairs, or thrown a ball, you'll know how easy it is to overcome gravity. The problem is, though, although it's a relatively weak force, it acts over long distances, infinitely long, in fact. So it requires an awful lot of energy to keep overcoming it and leave the Earth. So a rocket, therefore, requires a massive quantity of fuel in order to reach beyond the Earth, as we've seen, almost 20 times its own weight. But gravity is what gives things weight, okay? It gives weight to mass. It gives mass weight. Yeah, that's right. Mass and weight are two different things. Firstly, mass is a matter of how much stuff there is of something, okay? A mass is measured in kilograms. So the mass of an object is the same everywhere in the universe. So if I have, let's say I've got a kilogram of chocolate on Earth, I can take it anywhere in the entire universe and I will still have the same amount of chocolate. Well, assuming, of course, I don't eat any of it. However, the weight of the chocolate will vary because weight is a force. It's measured in newtons, named after Sir Isaac, and it depends on gravity. If there's no gravity, there's no weight. So to calculate the weight in newtons of an object, you need to multiply its mass in kilograms by the gravitational field strength, G. So on Earth, the value of G is 10 newtons per kilogram. So the weight on Earth of 1 kilogram is 1 times 10, or 10 newtons. Now on the Moon, for example, G is 1.625 newtons per kilogram. It's about a sixth of that on Earth. So that means anything, my chocolate bar, a kilo of apples, you weigh 1/6 of what you do on Earth when you're on the Moon. Your mass is the same. There's still the same amount of you, still the same amount of apple, still the same amount of chocolate, as long as I don't eat it, but it weighs a different amount. So my 1 kilogram chocolate bar is 10 newtons on Earth, but it'll be 1.6 newtons on the Moon. But I've still got 1 kilogram of chocolate. As you can see, if the young person in my little slide there has a mass 56 kilograms, then on Earth the weight is 560 newtons, but on the Moon it's 900 newtons. And that's the difference between mass and weight. That's an important thing to understand in science. Okay, so the gravitational field of Earth, that's what we call the force of gravity as it extends into space towards infinity. Oh, there's a little formula for you to work it out, by the way. So weight in newtons is mass in kilograms multiplied by G. So on Earth, we say it's 10 on Earth. It's actually 9.81, but 10 is close enough. So we can multiply. So, and that's at or near the Earth's surface. It also, that's how it's trying to accelerate things. Remember we said force and mass and acceleration were all linked. Then the acceleration due to gravity is 9.8 meters per second every second. That's what pulls you towards the ground. So the gravitational field on Earth extends out into space. And that's what we call it, the gravitational field. It reaches way out. It affects the Moon. It's what keeps the Moon in orbit. It reaches the Sun. The Earth actually affects the Sun. And it also interacts with the other planets as they do with us. As a fact, we said earlier, gravitational fields are calculated from infinity. That's to say gravity gets weaker and weaker, but only reduces to zero at an infinite distance away, at the other end of the universe. Of course, in reality, the gravitational field gets so weak that it doesn't have much of an effect, certainly not over great distances, and it's effectively dwarfed by other nearer celestial bodies. So by the time you get halfway across the universe, then the Earth's gravitational field is effectively zero, but it's not zero. Okay, and because it spreads out in all directions, gravity actually reduces by a factor we call an inverse square. That is, the further away you move, the force is reduced by a square of the distance. So if you double your distance, then the force is reduced by a quarter. So if we have an apple that weighs 1 Newton and we move it a distance of 1 diameter from 1 to 2, then the apple will weigh 1/4 of what it did at the Earth's surface. We move it another distance, the same as the first one, that's twice the distance. So it's 3 times the distance overall. The apple will weigh 1/9, then it will weigh 1/16, and so on. So we inverse square. That being said, let's take the International Space Station. Now, the International Space Station is in orbit around the Earth, and it is still, in terms of gravity, about 89% the gravity on Earth. Now, I hear you wonder on this one, why are the astronauts weightless on the International Space Station then? Well, they're not actually weightless. In reality, the astronauts on the ISS are plummeting towards Earth. It's just so is the ISS. It's a bit like when you drive too fast over a humpback bridge, or go for a ride on one of those really scary rides at the fair or adventure theme park, you know, when your tummy goes all wibbly wobbly. You can, if you have enough money, experience this yourself. Now in America, you can join a special flight in a jet airliner. And once it gets a few thousand meters above the ground, the pilot puts it into a steep dive. And for a few minutes, you and the aircraft falling towards the ground, it feels like you're weightless. It's also known as the vomit comet, which is a yucky nickname based on the effect that it can have on those who are not good at traveling. So looking at our astronaut floating in space, oops, let's go to that one. There she is, an astronaut in space. Why isn't that satellite going to crash into the Earth? Well, the thing is, the satellite is falling to Earth, as we said, but it's also moving forwards and just the right speed. So it's moving forward, so it never actually manages to get all the way down. It's a neat trick, really, and it allows all sorts of useful things to be kept up in space. So if you can imagine the satellite, the ISS, going round around the Earth, the gravity's trying to pull it down towards the Earth, but it's moving forward. So as it moves forward, it's staying at the same distance away from the Earth all the time. So it's in orbit, it's going round and round in a circle, more like an ellipse, but which is a sort of a squashed circle. But it's going round and round and round because it's moving forward at exactly the right speed to stop it crashing into the Earth. It's really handy because satellites are things, anything in orbit around a planet. That includes the moon. So the moon is a satellite of Earth. And it also includes all of the things that bring all amazing sort of things towards you. So your Sky TV, if you have Sky TV, the things that make your sat nav work, the satellite navigation, those that provide those amazing super images on the weather programs after the news. They help monitor the environment. They can also spy on other countries. Well, that last one is possibly a bit naughty, but you get the point. Satellites are, well, jolly useful. So all of these satellites are well within the gravitational influence of Earth and could all fall down. And as long as they're moving forwards, it's not going to happen. Now, of course, eventually the satellites will no longer be needed. They're switched off. And now they will fall back to Earth. But again, there's no need to worry. As they're small, they will not cause any damage. Why not? Well, as they enter the atmosphere, the air particles in the atmosphere rush past the falling satellite. The friction between them and the satellite heats them up. It's like rubbing your hands together incredibly fast. They get so hot. In fact, the satellite itself gets so hot, it actually burns up and it's destroyed before it gets anywhere near the ground. In reality, stuff's falling down to Earth all the time. mostly space rocks and such like. It's what so-called shooting stars are, burning up rocks and the occasional bit of space debris. Humans, eh? Wherever they go, they leave rubbish lying about, even in space. Okay, right, let's have a look at some practical stuff. Now, I'm going to see if I can start unmuting a few people now, because I think we're going to have a nice chat, if possible. That's that one. Unmute. Oh, got some sound back again here. We've got everyone in here. Let's have a look. Unmute and unmute. And that's it. Everybody's unmuted now if you want to chime in. So what I'm going to do is I'm going to run through some instructions. Now you can download these. All these instructions, as you can see, come from the BBC website. I do have a PDF version of this, so if anyone wants it, we can sort out next week about getting a copy to you between now and next week. But it's how to build your own rocket. It's going to work just the same as a real rocket, okay? I mean, it'd be really cool if you could build your own fully functioning rocket, right? And I think everyone's agreed with that one. Well, you can. You're not gonna need anything you can't find knocking around your house. So you probably won't even have to break the lockdown to get the bits, because I'm sure you've got most of this in the house already. Now, word of caution: this rocket won't actually get you into space, but, and this is the thing, it does work exactly the same way as a real rocket does. So it's a great bit of science, and there's a bit of chemistry to learn as well in there as well. So there you go, 2 for the price of 1. Now, as I say, you can download instructions from various internet sites. Just Google build your own rocket. Other search engines are available. But these are the instructions that I think work the best. And I can give you a link to them at some point. In fact, it's on the screen in a couple of slides' time if you want to write it down. But you can just search BBC build a rocket. Okay. I may try and put a video of it on my YouTube channel at some point as well, but I haven't got that yet, so don't rush over to see it. Okay, so now we know how to leave the planet. Let's see if we can build a rocket. Okay, let's have a look at our slides. So the first thing we're going to need, oops, where's our list of stuff? Oh, do you know what? I think I possibly didn't put the list of ingredients on there, but never mind. I can look them up. Let's just grab my list of ingredients. Photos. Okay, this is what you're going to need. Revert to original. You're going to need
a bottle.
A bottle, yeah, definitely need a bottle.
Pencil.
A pencil, you will do indeed. Revert to original. Here we go. An empty plastic bottle, okay? So you want a 500 ml or a 1 litre bottle. They work the best.
Coca-Cola bottle.
Yeah, perfect. Just make sure you drink all the Coke first or it won't work. You will need some white vinegar. Why white vinegar? Because it's better, it's purer, and also it doesn't leave a mess if it goes wrong. You'll need some bicarbonate of soda, sodium bicarbonate, which you should have in your cookery cupboard.
Yeah, soda.
Yeah, you'll need some straws or pencils for the legs. Straws work best, actually, because a cork or a rubber bung that fits tightly into the bottle, but not too tight. Some sticky tape, a piece of kitchen roll, and a spoon. Okay, so you will turn your bottle upside down. You tape your 4 straws to it, so it's nice and level. It should be about 2 centimeters off the ground from the net.
Dad.
Don't forget to decorate it, it says on there. You can decorate it. Tear off a piece of kitchen roll, 1 piece. So if you're using a 500 ml bottle, cut the piece of kitchen roll in half. Place 1 dessert spoon of bicarb of soda in the middle. Carefully roll the kitchen roll, twist each end so the bicarbonate soda is wrapped like a sweet. If the paper starts to unroll, dampen your finger ends and twist the paper again. But be careful, don't make it too wet. So if you're using a 1 litre bottle, do the same, except use a full sheet and 2 spoonfuls of soda. Okay, so now you pour the vinegar into the bottle until it's 1/4 full. Screw the top on until you are ready, and then take everything outside. Find a nice bit of level ground and test that your rocket stands up steadily. Best not to do it if it's too windy. Your rocket should shoot straight up quickly, so you're going to need to stand well back. 5 meters, that's 5 adult paces should be enough. So you get an adult to be the launcher. So you turn the bottle so the screw top is upwards. Take the top off and put to one side. You'll need to do the next bit really quickly, okay? So you slide the package of bicarb soda you made into the bottle containing the vinegar, holding the bottle as steady as you can, and quickly push the cork firmly into the bottle. Turn the bottle over, carefully place it on the launch pad, move back 5 paces as soon as you can, and just let science do the rest. Okay? Now, some safety advice. It's really good. It needs adult supervision and reasonable care. So if you live somewhere where the gardens are quite small, you may want to reserve this until you can get somewhere after lockdown.
In a park.
In a park, yeah, but fair away from, you know, not on a busy day. Okay. Okay. Follow the instructions carefully. You don't need any special safety equipment. These safety reminders are just there for the adult to make sure that it's carried out in a safe way. Okay. So remember, you've got to be at least 5 paces away when it's launched. Wash your hands thoroughly after handling the vinegar. Vinegar is safe, but it is an acid, and if you don't wash your hands and you scratch your eye or something, then
It'll burn.
it will definitely burn. Yeah,
Burn your eye.
it will. Place the vinegar bottle top as soon as you take the vinegar out. That's fairly so. You don't want to knock that over and get vinegar over everything. It smells as well, don't it? So as the rocket takes off, some vinegar will spray out. If any of it goes onto your clothes, wash it off immediately with water. And once you've done it, throw a bucket of water over the launch pad when you finish to wash away any vinegar. At the bottom of that screen is the web page to these plans. So there's a video on there as well to show you it happening. So if you can't or won't or don't want to do it for now, you can look at the instructions on that video. Okay. Right. So that's what you do for the safety advice. And you this again, they're all on the worksheet. What's going on in there? Well, here comes the science bit, as they say. Now, vinegar is an acid. It's called acetic acid, and it's dissolved in water. Bicarbonate of soda is a base called sodium bicarbonate. So initially, the reaction that takes place between an acid and a base makes carbonic acid, but that quickly breaks down into carbon dioxide and water. So the cork initially stops the carbon dioxide from escaping, but the pressure of that carbon dioxide being released builds up and up and up until the cork pops. The water and the gas escape. And as the contents of the bottle shoot downwards, then the bottle itself shoots upwards, demonstrating perfectly Newton's third law of motion. For every action, there's an equal and opposite reaction. The force of gravity has an effect as it is pulling the rocket down, but the pressure of the gas is pushing against gravity, so the rocket goes up. As the gas runs out, though, then gravity takes over again and pulls the rocket back to Earth. You're not going to get into space with this one. It's going to go quite a bit into the air, but it was going to come back down again. Okay, so you can experiment with what shape will make the rocket go even higher. What could you do to the bottle to make it go higher?
Make it bigger.
You could make it bigger, I suppose. You could streamline the shapes.
Make it more aerodynamic.
Yeah, you could make it have a pointy top or a round top. Have a look at a real rocket and see if you can improve the design. Okay, so there's a few things you can do building your own rocket. If it goes wrong, there are a couple of things that you may have messed up on. Don't go back to it straight away. It may be that it's just a slow reaction. It might take a while. If it's not taken after a few minutes, then throw an old coat or a large piece of strong cloth over it. Keep it at arm's length with the cloth covering the bottle. Pull the cork out over a drain and let the contents run away safely. It could be that the cork was not a tight fit, so the gas just escaped straight away. There was no pressure build up. It could be that the cork was pushed in too firmly and there was not enough, there was too much friction on the cork and the bottle for it to be released. Or it could be your vinegar was old and it wasn't acidic enough. So get some fresh vinegar. It could be that your package of bicarbonate soda was wrapped up too tightly and it didn't open. It could be that there was either too little vinegar or too little bicarbonate soda in there. Or it could be a combination of 2 or more of those above. Okay.
So you might need goggles, you know.
It wouldn't be a bad idea if you were doing it, if you just wanted to pop those on just to be safe and, you know, just make assurance doubly sure, as they say. Okay, so let's put this thing back on here because I just shut down something earlier. So here we go. Where were we? Yes. So let's go back to the bottom because I just need to finish the last little bit of. Right. Okay. Yeah. So you, as I say, you can download those instructions from the internet from various sites. Just Google build your own rocket. Go to that BBC link if you want to.
Yes, sir.
Or, yeah. So now we know how to leave the planet. We can look forward to exploring the solar system next, finding out what the planets are really like. Could we colonize Mars? What exactly is going on inside the sun? So hopefully I'll see you next week at the same time to find out all these things. So
Very interesting.
good, I'm glad you liked it. So any questions from anyone? I'll put people's pictures back up on the screen. Where are we? Let's put everyone up there. Oh, look at that. Amazing. Okay, I do have a YouTube channel, I think I already mentioned. You can go along. It's mostly GCSE physics and A-level physics, but I will do requests. There are a couple of things on there. So feel free to come and have a look at those.
Yes,
And I will see you next week, but we've got enough time now. These are time to last about, bang on time, about 3/4 of an hour of me talking. And the idea being we've got about 15 minutes, 10 minutes at the end to answer any questions or talk about stuff, okay? So it would be good to see you. We're going to, as I say, as we go forward, we're going to look at the solar system next week, then we'll look at galaxies, then the universe itself, and then looking at life and the universe, the life and death of the universe. And then finally, on week 6, we're going to look at time and how we measure it and how it isn't something that just runs in a straight line. It's not a linear thing. Time can change. We can slow it down. It can speed up. There's all sorts of interesting.
So how do people get down? How do you get back down?
Get back down from where? From space?
Yeah.
Well, you turn your rocket round, come back to Earth. Now that's the tricky bit, because when you come back into Earth, there's a lot of air. So you're in a vacuum. So you're moving quite nicely. And all of a sudden, you've got the atmosphere on Earth, and it's like almost like hitting a brick wall in a car. It's like well, that's a gas. Compared with the vacuum in space, it's almost like hitting water or something almost solid. And it's really dangerous. The re-entry point of a rocket is probably as dangerous, if not more dangerous, than the liftoff, because you're coming in at incredible speeds, you're hitting that air, and that air is rushing against the rocket, and the friction, you know what it's like when you just rub your hands together?
Yeah, it gets warmer.
Yeah, can you imagine doing that a million miles an hour?
I can do that.
Your rocket and the air molecules are going to heat the rocket up so much it actually burns up, and that's, as I said, that's what meteorites are. They're rocks, solid rocks that come from space, hit the Earth's atmosphere. There's so much friction it actually melts the rock and destroys it. And you can see, have you ever seen a shooting star or anything like that?
Yeah.
That is rock burning. That's how much it is. So, yeah, when you're coming back to Earth, what you have to do, there's a couple of things you need to do. You have to try and go as slowly as you can. You also have to cover your spaceship, the bit that hits the atmosphere first, cover it with special tiles, special material that resists heat. The bottom of the space shuttle had these special ceramic tiles underneath, and they used to heat up so much, and they're so good at stopping heat from passing through them. If you were to make a box out of them, you could make a cup of tea, put it in the box, put that box inside your freezer, and when you went back the next day to get your cup of tea out of the freezer, it would still be hot enough to drink. That's how good they are at insulating against the heat.
So who was the first person that came on space?
The first man to go in space was Yuri Gagarin. He was a Russian. They don't have astronauts, they have cosmonauts. So Yuri Gagarin. The first creatures in space were animals, to try and see if we could survive. They sent dogs up there and monkeys and various other animals. Not always did they come back. A lot of the time they ran out of oxygen and sadly died up there. But that's unfortunate. Yeah, Yuri Gagarin was the first man in space. Neil Armstrong was the first man to walk on the moon. He was an American astronaut. Yeah, So Yuri Gagarin. Any other questions? Or
Come on,
anything?
guys, give Sir some questions. He's bored.
Oh, are we on? See if I make sure everyone's not muted. No, not muted. Everyone's off mute. So if you're muted, it's you muting yourself.
No, good. No questions.
No questions.
No.
Can't believe that.
I'm good.
You're good. Okay, so next week then, the solar system. We're going to find out about the sun. Why it's so bright and hot. What's going on inside there? What else are we going to do? The planets. We're looking at some of the planets. Which ones are made of rock and which ones are actually made of gas? There are some planets out there that are just basically gas. We're going to look at planets where the surface is so cold you would freeze solid in an instant, and planets that you would fry. Planets that could almost have been like Earth, but something went wrong. And we're looking at what planets we might be able to build a base on one day and go and live on, and what problems that might hold. Then we're going to look at what happens to the planets as they go around the sun. We'll look at why we have a summer and a winter. We'll be looking at why the Earth has to be where it is for us to exist. We'll be finding out about something called the Goldilocks zone. What else will we be finding out next week? Loads of stuff about our solar system.
Yeah, stuff.
Yeah, and our solar system itself, we'll be working out how far. I'm going to show you, if you can imagine the distances involved, we're going to scale it down. So we'll say things like, if the sun was the size of a football, where would everything else be? How far away and how big would it be? And you'll be amazed at the distances involved. And yet, you could fit all of the planets, if you were to line them up next to each other, you could fit them all between us and the moon. That's how much the planets are, but they stretch over millions of miles. And we're going to be looking at why Pluto is no longer a planet, why it's dropped off. What else are we looking at? Yeah, that'll be good. And then we're going to look at our sun and where it sits in the galaxy and what a galaxy is and what's at the center of the galaxy, things like that. And then we're going to look at where the galaxy is in terms of all the other galaxies, the expanding universe, and then a little bit about life and what's out there, as I say, and then finish off in week 6 about time. So, who found today interesting? Who's coming back next week?
I'm coming back next week. I don't care, so it was really good.
Good.
Yeah.
You're more than welcome. Yeah, same.
See you next week.
Brilliant. If there's anything you want to know as well, bring the questions along next time. I'm not sure how you can contact me directly. You can always go through my YouTube channel. And if you want me to cover anything, if you want to make sure that something's included, then you can drop me a little message and say, oh, when we do galaxies, can we do this? Or can we find out about that? I will do my best to answer all your
So
questions.
I'll write it on your comment on the video.
Yeah, that'd be brilliant. Fantastic. Yeah, and if you want that sheet, I can send you a PDF version of it. But I don't want any angry parents complaining because I've made their house smell of vinegar. So be careful. Okay, make sure you do it in the garden.
Yeah.
Okay, right. If there are no more questions, anybody like me to go over anything again? Whoops.
Yeah, so I think we're good, yeah.
Okay,
Yeah.
brilliant. It's been real fun, guys. I've really enjoyed it.
Thank you. Me too, sir.
Yeah, and I will see you all at the same time next week, and we'll
Yes,
be
sir.
finding out about the solar system.
Yeah.
See you later, sir.
A bit.
Thank you.
Okay, you're welcome. Bye.
See you.
Adios.
A bit.